Hello everyone, this is section 1.7, combination of functions. Our goals here are going to be to understand how we can combine functions using basic arithmetic rules that we've seen in the past. So, if we have two functions we'll call f and g, their sum, difference, product, and quotient are the functions whose domains are the set of all real numbers common to the domains of both functions. So the big issue here, thing we need to really pay attention to, is the domain of these functions, right? Where do things go wrong, right? If I want to add, subtract, multiply, or divide any of these two functions together, I just need to be careful about two things, right? Real numbers that cause domain issues. The first one is dividing by 0. So if we have a 0 in the denominator, that's something where we have to be careful. That's a time where we have to be careful about domain. Specifically, it's going to happen quite a bit when we take the quotient of two functions. Any values that would make, in this case, g of x equal to 0, would be excluded from our combined quotient function. The other issue when it comes to domain is if we have a negative inside an even root. For example, if I got a domain that resulted in the square root of -3, that is a non-real number, so we would exclude that part of our domain. So when we talk about domain, the two big rules to follow, rules to pay attention to, things where locations where things can go wrong, is if I have a 0 in the denominator and if I have a square root or even indexed root with a negative inside. So I'm going to walk through one of these examples. Sorry, I'll do 1 and 2, and then I'll let you guys try out 3 and 4. So we're trying to identify the domain of the following functions. So f of x is x squared minus 7x. That's a quadratic function. Its domain is unlimited. And the way we show that in interval notation is we go from -infinity to +infinity. Those rounded brackets indicate that the endpoint, in this case -infinity and +infinity, are excluded from the data set. Let's look at another one. Here I have f of x equals the square root of 3x plus 12. Well, I need to account for the situations in which this quantity, 3x plus 12, well, that value must be greater than or equal to 0. I know that based on the work we did with square roots last year. So I'm going to solve for x, right? 3x is greater than or equal to -12, which means x must be greater than or equal to -4. So that's not an interval notation, but it does represent our domain, all values greater than or equal to -4. So the way we denote that in interval notation, because -4 is included in our interval, we're going to use that square bracket, and then the interval continues on to infinity. So as we usually do with these notes, I'd like to ask you guys to pause now and try examples 3 and 4. If you're not really sure, just keep following the video. I'm going to come back and explain my work in just a few seconds. All right, let's jump down to number 3 and see how we did. On this example, we have x minus 3 divided by x squared minus 2x minus 3. So what I'm thinking here is that I have a denominator. So I just have to watch out for any cases where that denominator equals 0. So as you can see here, I just set that whole denominator equal to 0. Before we can do anything to solve, recognize that we're dealing with a quadratic. And if we have that quadratic set equal to 0, not equal to 0, I get it, but equal to 0 fundamentally, we can solve this through factoring. So you can see there, I've identified the two values here that x must not equal, 3 and -1. So when we write our solution, our domain here, you can see that in the box here. We always write our intervals going least to greatest. So you'll notice I go from negative infinity to -1 to -3 to positive infinity, right? We always want to work sequentially from most negative to most positive. The way this basically what's going on here on our number line, we have two places, right, at -1 and at +3, where we are excluding our domain. So what our domain really represents, it represents this section over here and this section here and this section over here. The way we say that mathematically, perfect language here is we would say in union with, that U there is in union with, because we're really combining these three different intervals to represent our domain. All right, let's keep it moving here. Here in the next section, we are given three functions: f of x, g of x, and h of x. I know we've seen this before. I'm going to walk through just two examples just so you see them, 5 and 6. And again, you'll try 7 and 8. What are they really asking for? Well, on the first one, there's two ways we can approach this. We can find f minus g of x and then substitute in +2. And I think that might be the way to do it. So I'm going to go ahead and do that. I'm going to take f of x, which is going to be 2x minus 1, and I'm going to subtract from that x squared plus x minus 2. What we're really going to create is f minus g of x, a new combined function. So let's combine our like terms. We're going to end up with negative x squared. 2x minus x is plus x. -1 plus 2 is +1. What we have here, let me rewrite that, f minus g of x. Now we have this new function. All we need to do to evaluate f minus g of 2 is to plug in 2 for x. So f minus g of 2 will be -2 quantity squared plus 2 plus 1. So we have -4 plus 3. So f minus g of 2 is -1. You know what? I think we get I get the sense you're going to be okay with this. So I want you to go ahead and try 6, 7, and 8 on your own. I will obviously work these out for you, and we'll check in to see how we're doing. But I definitely want to let you guys try these on your own first. Let's see how those problems came out. So if we look at number 6, what they're asking us for is to combine, but not evaluate, the sum of f and h. So all we're doing here is adding these two binomials together. Notice something, I like using parentheses when I'm combining functions. I like to do that for organization's sake. It also reminds me, if, for example, this were negative, to distribute that negative appropriately. So I like grouping my functions together with parentheses just to remind myself of those rules. On to number 7. So they want g over h of 11. And I bet you some of you just plugged in 11 into x squared plus x minus 2, and you went and got 121 plus 11 is 132 minus 2 is 130. I don't think that we need to do all that all that arithmetic. I'd prefer algebra. So what I did is I tried to identify g over h of x. And what I found is I was able to simplify that. I was able to factor my numerator and cancel one of our binomials. I need to account for that, right? When I simplify, I know x can't equal 1. It would cause some domain issues. But evaluating x plus 2 when x is 11 becomes much, much easier. So there are definitely circumstances where if we put a little bit of work up front, it makes the actual evaluation significantly easier. Finally, over on to number 8. This is telling us to multiply functions f and h together. and that's what I've done. You know, you guys may have called it foiling. We are distributing these binomials and expanding and combining. Let's move on to composition functions. All right, I just wanted to kind of pause for a second here and write all this out. I know we've seen composition functions before. I personally don't love this notation, the FOG, that FOG or whatever. What that's really saying is it's really saying take as an input x and get an output g of x, use the output of g as the input into f, okay? So we're generally gonna work inside out here, right? What x? So when we talk about the domain of a composed function, first, this x must be part of g, right? The innermost function must be defined. And then any values where for x that make this whole quantity plug into f and cause values where the domain has been excluded must also be addressed. So when we talk about the domain of composite functions, the innermost function must be defined, and the output from that innermost function must create a defined function in the outermost function. Let's look at some examples and see what we can do. So first, we're going to start with f of g of x. So we're going to take g and plug it into f everywhere we have an x. So instead of the x there, we're going to plug in all of g. X squared minus 2x plus 6 plus 1. This is FOG of x. I want to simplify this. Standard form's always preferred. I'm going to distribute that 2. I'm going to get 2x squared minus 4x plus 12 plus 1 gets us plus 13. As we look at the domain here, we are dealing purely with polynomials, right? Linear and quadratic. So there's no domain restrictions, right? That's going to be negative infinity to infinity. They also ask us to find g of f of 1. Now, one thing to note about composed functions is they're not a two-way street. F of g of x is very rarely the same as g of f of x. So we got to do some work. This is telling us to take g as we're going to take f of 1 as an input into g. So f of 1 is going to be, well, what do we get when we plug 1 in for f? So if I plug in 2 times 1 is 2, plus 1 is 3. So we can replace that f of 1 with 3. Really, we're just looking for g of 3, right? So I'm going to plug in 3 into g. 3 squared is 9 minus 2 times 3, well, that's 6. So when it's all said and done, g of f of 1 was the same as g of 3, which was, oh, I think I made a small mistake there. This should be a 6. Sorry about that. And we're left with just regular old 9. We are going to look at 2 rational functions next. I think it's worth giving it a shot. See what you guys can do. See if you can play around with some of the domain issues that may occur with these fractions. All right, team, let's check out 4, 5, and 6. So here on number 4, we are looking for f of g of x. So we're going to take g, the whole function, and plug it in wherever we see an x in the function f of x. So you can see here, this x in f has been replaced with all of 3 over x. And then I simplified my denominator. I created a common denominator within my denominator and then multiplied by the reciprocal to get my simplified form of 2x over 3 minus x. On number 5, I perform a similar process, right? But we're flipping the inputs and outputs here. We took all of f of x and plugged it in wherever we had an x in the function g. And again, we simplified. The tricky part here, especially when we're dealing with fractions, is domain. Remember, and I'm going to just scroll back up here, we need to first identify values that would not be in the domain of our inner function, in this case g. So if I look at number 4, what values would make this function here, g of x, undefined? Well, I know that our denominator must not be 0. So that's where this is coming from. I also need to exclude values of x where the result, g of x, would not be in the domain of f. Well, the easiest way to approach that is to look at our resulting function. I can see here I have a denominator, and x must not equal 3. Right? I need for my function to be defined throughout, so that's where my excluded values come from. We use interval notation here, and that's what it'll look like. Negative infinity to 0, in union with 0 to 3, in union with 3 to infinity. Number 5, we follow the same process. What values would make f of x as the inner function undefined? Well, x can't equal 1. And then the resulting function, well, in this case, that is defined everywhere. So the only restriction we have is that x must not equal 1. There you can see our domain. Finally, we are going to build some of our own composed functions. Basically, you will be given a composed function, and you want to decompose it into its parts. So what do we want to do? We always want to work inside out, right? I think that's a good idea to have in your head when we're dealing with composed functions. Inside out, innermost, then outermost. When we do that, we want to identify parent functions, but we want to avoid specifically f of x equals x. It doesn't really get us very far. So what do I mean? Here we have, I would say, 2 functions. They're telling, they would even tell us here, we have a result. H of x is f of g of x. So we're looking for f of x and g of x. As I said, we want to work inside out. In this case, this FOG notation, I learned this a million years ago in a different format, looking like this. These are equivalent statements, and you can see a little bit more clearly the innermost function here will be g of x. So what is going on inside these parentheses here? Well, that's going to be g of x. G of x is going to be x minus 1. What else is going on? Well, we have this whole thing being cubed. That's our outer function. F of x must be x cubed. If we wanted to compose this to check our work, we could take all of g and plug it in where we have an x in f, and we can see that we get back to where we started. Let's look at another one. Here I have h of x, and I'm looking for f of x and g of x. I want to go innermost to outermost. The first, if we think about order of operations, the first thing that would happen here is that x would be cubed. And the second thing that would happen here is that whatever quantity it's added for. Whatever quantity we get, we add 4 to it. There's one last one here, number 9. We have j of x, and you can see that we want to create a composed function made up of 3 components, f, g, and h. So we know, f of g of h of x is really what we have. So h of x will be our innermost function, g of x will be next, and f of x will be last. So our innermost function here is x squared. I can see that happening there. Think in order of operations. X minus 2 is next. That's really representing what's going on inside the radical. And finally, the outermost function is the cubed root. Notice that for 7, 8, and 9, overwhelmingly, these are parent functions that we saw earlier in the unit. Nice work, everybody. Way to hang in there. See you next class.